So we're going to talk about Chapter 3 definitions in this video. This is the terms and concepts from the end of Chapter 3 of your textbook. There's a lot of terms here, so I'm going to skip over some of those that aren't so important for you in this class. I'm going to try to keep this to about 15 to 17 minutes, so we'll skip over a few of these. The first one is absolute dating. This is just a way that we determine how old things are, and there's a variety of different ways. One of the main ones is what's called carbon dating, but not a lot you need to know about this term. Asthenosphere is a layer of molten rock that is under the outer surface of the earth. So if you've ever seen like a volcano, or anytime you have lava coming up out of the Earth's crust, that is coming from the asthenosphere. So the asthenosphere is kind of, I think of it like a gelatin, like Jello, but it's essentially rock, kind of Jello rock. The next term is basalt. Basalt is a very specific type of rock that comes out of the bottom of the ocean. So again, if you've ever been to an area with active volcanoes like Iceland or Hawaii, there are a lot of black rocks, and they're very sharp too if you've ever seen them. And these are basalt. Basalt is one of the most common rocks in the bottom of the ocean. We'll talk about why that is in class. Body wave, don't need to know that. Buoyancy is anytime something floats on top of something else. So things are buoyant. So a good example would be, a ball floating in water. The ball is buoyant in the water. And buoyancy is used a lot in explaining why things happen the way they happen on Earth with rocks. And we'll talk about buoyancy and density. Catastrophism, don't worry about that one. Conduction, that is the situation where heat is transferred indirectly. So for example, if you think about my coffee cup that has hot coffee in it, if I put my hand here, heat is being conducted from the cup to my hand, right? You can feel the heat from the coffee. It's hot in the cup, and that heat is being conducted to my hand. And that's one way that heat is transferred between things. Continental crust is essentially the earth we walk on, right? So the earth is composed of many layers. One of those layers, the outermost layer, is continental crust, and we'll talk a lot about that. Continental drift is not really a good way to describe what happens, because it's not really drifting that you would think about. So drifting in the English language is things that just kind of float along, right? So you think about like on a lake or an ocean, if you have a boat, a sailboat, it'll just drift, right? It'll just kind of move along the ocean. Continents don't do that necessarily, but it refers to the fact that plates of continents, continental plates, move. And they move in very specific ways, which is why I don't like the word drift, but that's the term we'll use. Convection is another type of way similar to conduction. So conduction and convection are two ways to move heat. So convection is a little bit different. So imagine I have, imagine this is a pot of water, and I have heat, a fire under my pot of water. What happens is the heat from this fire is heating the water in this part of the pot, right? And then what happens inside the pot is the water moves kind of like this, right? And that's called convection, right? The warm water is moving inside of the pot. And you can watch this, if you're cooking dinner or lunch and you have a pot of water, you can watch how the water boils, right? And it moves. That is convection, and that's moving heat throughout the pot. Convection current is just the current that's created by convection. Convergent plate boundary, this is a very important term I want you to know. This, we talked about continental plates before. Continental plates, real briefly, is essentially parts of the crust that form these large plates. So you can think of the surface of the earth as a jigsaw puzzle, right? We have, I forgot how many, 50, 60 different pieces, and they all move and they all bump into each other. Sometimes when they bump into each other, they go towards each other. This is called convergence, right? Convergence. This is very different than divergent. Divergent is they're moving apart from each other. We'll talk about how that happens, right? So convergent, coming together, divergent, moving apart. Definitely need to know those two terms. Those are really important. Core is the center of something. So if you think about an apple core, right, the center of the apple, but also the earth has a core, right, the center of the earth. Crust is another way to talk about the outer edge of something. So the earth has a crust, right? We talked about that just a little while ago with continental crust, right? Essentially the same thing. Decompression melting, don't worry about that one. Density is anything, is when two things or things differ in terms of essentially how many molecules are in there. So a good example, I don't have any on my desk right now. So imagine I have some rocks and some flowers. The rocks are heavier, right, than the flowers. The reason is there's more molecules that make up the rock per unit area. And the unit area we use is what's called a cubic centimeter, right? So if you take 1 centimeter and you essentially make a cube out of it, that's 1 cubic centimeter. So a rock has many more molecules per cubic centimeter than a flower, right? And because of this, they feel different in weight. Density is why that they feel different in terms of weight, right? So if you compare, I don't know, something that's really light. I can't think of a good example right now. Density, how many molecules are in a specific area. Now, this is important because things stratify according to their density. So a good example is, let's say I have a cup of coffee and I pour cooking oil, like vegetable oil, into it, right? The oil will not mix with my coffee, right? Because of the density difference. It's a stratification. So if you've ever seen, let's see, let me think of a good example. There's like a salad dressing. It's like an Italian herb dressing. It's essentially herbs, like plants, and oil, and some other liquids. If you pick up a bottle at the grocery store, you can see the different layers, right? Because the bottle has sat there and the layers have stratified. They've separated by density. But if you take that bottle of salad dressing and you shake it up, right, before you pour it on your salad, it's all the same. But if you let that bottle sit on your shelf for a week or a month, the layers will stratify or separate again because of density. Divergent, we already talked about that one, kind of the opposite of convergent. Earthquake is anytime the surface of the earth moves, and there's a variety of different ways that can cause that. And we'll talk about those in class a lot. But earthquakes are anytime you can feel the ground move or shake. So if you've been to California or Japan or New Zealand, where it's a lot of activity with the plates, you'll feel earthquakes. And they can be kind of scary. I've been in a couple, not big ones, I've been in some medium ones, and they can be kind of scary because everything around you is moving, right? Everything, cars, buildings, is really kind of scary, I think. Echo sounder, these are ways that we use sound in the ocean to determine how deep or how far something is away. So if we're on a ship and we want to know how deep the water is, we can take a sound, usually one we can't hear, is higher pitched, and you produce that sound and it hits the bottom of the ocean and it echoes, right? It echoes, it comes back. And by knowing the speed of that sound and how long it takes, you can figure out how deep the ocean is. So echo sounders are a really easy way. Some problems with it, but it's a fairly easy way to figure out how deep the ocean is. Fault is any kind of crack in the surface of the earth. There's lots of faults. Yeah, lots of them. Granite is a very specific type of rock. It's very common on land. So for example, if you ever see, I don't have any here, it's kind of a gray rock, it looks kind of peppery, like someone took pepper, like the spice, and put on it, the black pepper. It's really quite beautiful. So if you're ever in Columbia, South Carolina, our State House, which is near the campus, is made out of granite, and it's a beautiful building. And a lot of buildings are made out of granite because it is fairly common and it's really strong, but granite's an important rock. Hotspot is a very specific term when you have lava that is very close to the continental crust. So another way of thinking about that is with the asthenosphere, it's very thin. So the continental crust is a layer, and under it is the asthenosphere. Now, where the continental crust is thin, the asthenosphere kind of pokes through a little bit. And these are called hot spots. So if you've ever been to Yellowstone or you've been to Hawaii, those are hot spots, or Iceland even, those are hot spots as well. Isostasy, not terribly important because it's kind of like isostatic equilibrium. What you need to know about these two terms is if you look at a metal boat, metal shouldn't float, right? It's more dense, it's heavier than water, so metal boats should sink. The way metal boats float is the volume, the area inside the metal boat is greater than the weight of the water that would fill that. So what that means is the boat, the density of the boat is actually very low, even though it's made of metal, because of the amount of water that is displaced or moved out of the way by the boat, right? So if we built a really narrow metal boat, it would probably sink. But if we built a very broad, tall metal ship, like an aircraft carrier or a cargo ship, right? Those are big and heavy, but they displace or they move out of the way a lot of water because of the volume. And that's how they float. And that's called isostatic equilibrium. Isotope is a chemical, it's essentially a type of molecule that allows us to answer questions about where things come from. We can look at the chemistry of things. So you can use isotopes to see how old typically how old things are, or how things move throughout the earth or the ocean. Lithosphere, litho just means rock. Lithosphere is kind of another term for continental crust, which is another term for crust, right? So you can see a lot of these terms are the same, they're redundant. I don't know why they do this, but they do. The lower mantle is a specific part of the asthenosphere. It's kind of the bottom, if you will, the lower part. It tends to be very more hot. Magma is just a term for lava that is still underground. So if you ever watch the videos of those beautiful volcanoes in Iceland erupting, that's lava. But when it's underground, it's magma. That's all that is. Magnetometer is all rocks. Let me think. Most rocks that I can think of have metal in them. And what happens is when they're liquid, that those metal molecules are moving around. But when the rock cools, those metal molecules are locked in place. And the way they're locked in place is oriented according to the North Pole and the South Pole, the magnetic North Pole and the magnetic South Pole. And you can take this instrument called a magnetometer and look at a rock and see which way north and south were when that rock cooled. And that's really important for understanding how the earth works. We'll talk about that more in class. Boy, this is a lot of terms. I'm really sorry about this. A lot of stuff here, unfortunately. So we'll keep going along. Mantle is a specific part of the asthenosphere. Mantle plume, not terribly important. Magnitude scale, moment magnitude scale. This is essentially how we measure earthquakes, right? So if you ever hear of an earthquake of a 7, that's very different from an earthquake of 2, right? So it's the scale. Oceanic crust is similar to continental crust, but it's at the bottom of the ocean. Ophiolite, don't worry about it. P wave is a type of wave in earthquakes. It is similar yet different, obviously, from an S wave. So you don't need to know the details, but it would be useful to know that P waves and S waves are in earthquakes, right? So earthquakes generate waves, and those waves travel through the earth. And we can answer really interesting questions by looking at those waves. All right, next term, super important. Pacific Ring of Fire. So around the edge of the Pacific Ocean essentially the edge of the Pacific Ocean, there's a lot of activity, a lot of volcanoes, a lot of earthquakes. It's called tectonic activity. A lot of stuff happening, which is very different than South Carolina. We're not tectonically active. It's pretty quiet, honestly, off the coast here. It was called the Ring of Fire because volcanoes, it's hot, right? Lava, fire, right? So around the edge of the Pacific, there's a lot of volcanoes. And the Ring of Fire was really one of those things that scientists looked at and said, there seems to be a correlation, a relationship between the Ring of Fire and volcanoes and earthquakes. And there is, right? They fit together just like this. And it helped understand how the earth works. Paleomagnetism, not super important, but we talked about using magnets to understand rocks. Paleo just means in the past, right? So we can look at rocks from millions of years ago to see how the Earth's magnetic field has changed. Pangea is when all the continents on Earth were together, right? So now they're separate because of continental drift, but in the past they were all together, right? So it's kind of supercontinent, if you will, just one thing, right? Panthalasia, because there's one continent, it means there's one giant ocean. Plate is, kind of think about it like a piece of a jigsaw puzzle. So I mentioned Earth has about, I forgot how many, 50 or 60, some big number of different plates. And these plates move and they bump into each other. And these plates are made out of continental crust and also oceanic crust. We'll talk about how they move. Plate tectonics is how these plates move, right? So they move and they bump into each other or they move apart. Radiometric dating is essentially how we use isotopes to determine how old things are, right? So if I look at a rock and I know I can look at its chemistry and its isotopes, I can tell you how old it is. Radioactive decay is part of radiometric dating because all elements, all radioactive elements, decay at a specific rate. And by knowing that rate, you can determine how old something is. Relative dating, when you compare something to something else, right? So if you have a rock that is 5 million years old and it looks like this and it has certain characteristics, and you find a rock somewhere else that has the same characteristics and same isotopes, probably the same age, right? Relative dating. Rift Valley is where it's a very specific term associated with divergent plate boundaries, but it's essentially a valley that's formed by two plates moving apart. So when plates move apart, they diverge, but it creates a little valley between them. And there's one in Africa, it's called the African Rift Valley. That is a good example of that. We talked about S waves already. Seafloor spreading is just, a lot of these terms are just redundant. It's essentially what happens at divergent plate boundaries. The seafloor is spreading apart, divergent. That's all that is. Seismic waves, these are S waves and P waves. Those are waves that travel through the earth. Seismograph is how we measure seismic waves. Right? We have instruments called seismographs that actually measure the P and the S waves. Shadow zones are areas of the earth that don't have S waves and P waves from earthquakes. And there's very specific reasons why. And these are called shadow zones. Spreading center, essentially the same as divergent plate boundary. Spreading center, they're spreading apart. I think we have 10 different terms to describe the same thing. Right? So subduction is another way of talking about convergent plate boundaries. So when plates are coming together, depending on density, one of them will subduct or go under, right? It subducts, so they go together. This is less dense. Sorry, this is more dense, and it goes under. Subduction zone, where that subduction happens. Superplume, it's like a mantle plume, but really big, so they call it superplume. Surface wave, not terribly important right now. They're essentially just, I believe those are S waves that travel in the surface, but not terribly important. Terrain, we'll talk about that when we get to sediment. I wouldn't worry about it right now. Transform fault is a term, I don't have it highlighted here, but it is important. So we talked about convergent, divergent, right? So when plates come together, divergent. When plates move together, when plates come together, it's convergent, divergent. And there's another type of plate. So if you look at plates, instead of hitting each other this way, they move against each other. Those are called transform faults, right? Transform faults. A good example is the San Andreas fault in California. That's a really popular, well-known transform fault. Where transform plates meet, that's the boundary. Don't worry about uniformitarianism. I can't even say that word. Alfred Wegener, he was a scientist in the 1930s, I believe. He was not very popular, let's just say. And he came up with this idea of continental drift, which ultimately led to the idea of plate tectonics. But at the time, he couldn't explain it, right? He saw what was happening, but he couldn't explain it. He didn't know about all this other stuff we just talked about. And so he wasn't very popular, but he was right. He just couldn't explain how. And John Wilson, don't worry about him. All righty. So that is the end, whoo, of all the terms for chapter 3. So hope that was helpful for you all, and I'll see you in class.